Hi everyone, welcome back to chemistry. In this video, we're going to start chapter 8, which is all about solids, liquids, and gases. So we've talked a little bit about solids, liquids, and gases in previous videos, but we're going to go more in depth in this chapter. So we know that temperature and pressure can affect when substances change phase, right? If we add enough heat in and we raise the temperature on some substance, we can go from solid to liquid or liquid to gas. And I apologize again for my voice. I'm still recovering from that cold. But we can change the temperature, and that can change the phase of our substance. Pressure can also change the phase of our substance as well. If we increase the pressure or decrease the pressure, that can affect when our substances are changing phase. But what's interesting is that each substance has its own unique melting and boiling point. And what we want to explore in this video is why. Why does that happen? Why doesn't every substance just boil at 100 degrees Celsius or like water? Or why doesn't it freeze at 0 degrees Celsius? You'll notice on this chart here, which you don't need to memorize, there are a bunch of substances listed, and their boiling and melting points are very different. Okay, water we're familiar with, right? Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius, right? But these other substances are very different. So we want to know why is that. So it turns out that boiling and melting points for any particular substance depends on the strength of intermolecular forces, or forces between different molecules in that substance. There are several types of intermolecular forces, and I just want to list them before we talk more about what intermolecular forces are. But there are a bunch listed here. So going from the top to the bottom, we are getting stronger forces. So we have London dispersion forces at the top, dipole-dipole forces, hydrogen bonding, and ionic bonding. Now, we talked a little bit about ionic bonding already, right? And that is the strongest of these intermolecular forces. But there are these other forces that do exist, and the more forces that a molecule exhibits, the stronger the intermolecular forces are between those molecules, and the higher the boiling point. And we'll talk about that in a little bit. So there is a difference. Sometimes students get confused between these two different words because they look very similar. But there is a difference between intermolecular forces and intramolecular forces. Intramolecular forces refer to forces between the different atoms in our molecule. So this would be an example of an intramolecular force, the force between the hydrogen and the chlorine there, keeping that molecule together. An intermolecular force, and that's what we're going to focus on in our class, is when you have a force between two different molecules. Okay, two different molecules. So let me write that down. Between two different molecules. So we're going to focus on intermolecular forces in our class. And the first of those intermolecular forces that I want to talk about are London dispersion forces. And they're London dispersion forces specifically because they're named after the German physicist Fritz London, who kind of did a lot of work with this. But these London dispersion forces, or dispersion forces, they're very weak. Okay, they're very weak. They're the weakest on our list of forces, right, up here. But they do exist. And in fact, all molecules experience these dispersion forces. So anytime I ask you if a molecule exhibits any intermolecular forces, or if I ask you to list all of the types of intermolecular forces displayed, you are always going to say London dispersion forces. So these, what are these London dispersion forces? So anytime you've got some molecule interacting with some other molecule, right, there are electrons that are in that molecule. But those electrons, they move around, right? They're really, really tiny. They're moving around our molecule at all times. And what can happen is if at one snapshot in time, there are electrons kind of hanging out more so on that side of that molecule on the right. And on the other molecule on the left, we've got electrons hanging out on the opposite side. Then we can create this kind of snapshot, at a snapshot in time, we have this kind of really quick attraction between these. Remember, this means partial, right? That's our delta, partial. Our delta sign means partial. They're attracted to each other with these partial charges. Remember that this is different from when we have some kind of dipole, and we're going to talk about dipole forces in a little bit. This is different than a permanent dipole, where electrons are always hanging out near your most electronegative atom, right? This is just happening at a snapshot in time. It's a temporary separation of charge that disappears almost as soon as it appears. So that's why every molecule is going to display these London dispersion forces, because at any given moment, there will be electrons kind of hanging out in different regions. And if they all happen to be on this side and this side, we create that difference in charge right here, and we can get some attraction happening. And that's called a London dispersion force. Now, this is different from a permanent dipole. So dipole-dipole forces are the next one that we want to talk about. So we talked about covalent bonds previously, and we said with covalent bonds, that's the sharing of electrons, right? But we can have covalent bonds where we share electrons evenly, and we can also have covalent bonds where we don't have electrons being shared evenly or equally. And when we have that unequal sharing of electrons in a covalent bond, we call that a polar covalent bond. So remember, we talked about how in these polar covalent bonds, you'll have one atom that is more electronegative than the other one, so something like fluorine. And remember, we said the general trend on the periodic table is this: as you go right and up on the periodic table, our electronegativity increases. So fluorine's all the way over here, hydrogen's all the way over here. So fluorine's more electronegative, so it's going to hog all of those electrons. And I used the example of fries, right? It's going to hog those fries. Even though you're technically sharing them, fluorine's kind of hogging all of them. And hydrogen's going to have much less electron density. So what will happen is we'll get those electrons hanging out over here mostly, and that's going to contribute to a partial negative charge. It's not an instantaneous one. This is like those electrons are hanging around fluorine permanently, okay? More so than hydrogen. Still shared, but unequally. And we call that, right? We said we could draw dipole arrows where the positive end of the arrow goes with the partial positive side and the negative end of the arrow goes with the side with more electron density. And we called those dipole arrows. Dipole arrows. So that's where this dipole-dipole force gets its name from. When a molecule that has a dipole, okay, something like HCl or HF, like we have up here, right? When that molecule that has a dipole interacts with another molecule that has a dipole, a permanent dipole, they're going to be attracted. The partial positive end of one molecule can be attracted to the partial negative end of the other molecule, and this can create this dipole-dipole attraction. And this is a stronger force than the London dispersion force. Now remember, because the London dispersion forces, right as this attraction is happening between these two molecules, it's also leaving. It's not happening anymore because those electrons are going to start moving around, right? So once those electrons move away, this no longer has an attraction, right? So these are weaker than our dipole-dipole, where we have a permanent difference or separation in charge that's attracting those two molecules together. So that's London dispersion and then dipole-dipole. The next one is hydrogen bonding. So hydrogen bonding is stronger than dipole-dipole, which is stronger than London dispersion. And hydrogen bonding is really interesting. So any molecule that has hydrogen atoms bonded to electronegative atoms, such as O, N, or F, they tend to exhibit these really unusually strong intermolecular interactions due to this particularly strong type of dipole-dipole attraction called hydrogen bonding. So I have a little way of memorizing this, and it's is hydrogen, you have to ask yourself, is hydrogen on the phone? Is hydrogen on the phone? So anytime you're wondering if a molecule is capable of hydrogen bonding, you want to ask, is hydrogen on the phone? Is hydrogen bonded to fluorine, oxygen, or nitrogen? These really electronegative atoms. And if it is, if hydrogen is bonded to any of those three atoms, then it is capable of hydrogen bonding. So for something like water, for instance, those hydrogens are bonded to oxygens. So is H on the phone? Yes, H is on oxygen. Okay, H is bonded to oxygen. So these water molecules are capable of hydrogen bonding. And we depict that hydrogen bond, and some of you might know this from biology, we depict that hydrogen bond between something like oxygen and a hydrogen on another molecule as little dots connecting those two. All right, so let's practice identifying whether molecules exhibit these different forces. So remember, they can exhibit as many of these forces as they can, okay? So you can have, for a molecule, you can have it exhibiting London dispersion and dipole-dipole and even hydrogen bonding. It just depends if they, if they meet all of the criteria for these different types of forces. So for O2, let's try to list together what types of forces it can exhibit. So dispersion forces, dipole-dipole, or hydrogen bonding. So for oxygen, does it exhibit dispersion forces? Yeah, everything just exhibits London dispersion forces. So I often abbreviate London dispersion as LD. All right, now to think about dipole-dipole, I'm just going down the list here. Oxygen bonded to itself. Now, when we look at this oxygen molecule, and I've drawn the Lewis structure pretty quickly here, but you can look it up or just kind of think about it conceptually. When we're trying to figure out if something is a polar molecule, polar or not, we want to think about the electronegativity of the various atoms in that molecule. So I've got oxygen bonded to another oxygen. So what's the difference? What's the difference in electronegativity here? Yeah, 0. Because why? They both want electrons the same amount, right? They both have the same electronegativity value, okay? They're both in the same spot on the periodic table. An oxygen atom's going to want electrons as much as any other oxygen atom. Okay, so the difference in electronegativity is 0, and this would be a nonpolar molecule, right? Remember, I said anything bonded to itself is a nonpolar molecule. Okay, so this one, it doesn't exhibit dipole-dipole forces because it doesn't have a dipole, right? So no dipole forces. What about hydrogen bonding? Well, I don't even have a hydrogen here, right? So yeah, it can't hydrogen bond. So the only force, intermolecular force that this molecule exhibits is London dispersion forces. Okay. All right, now for HF, let's see. What can we write down right away? Yeah, London dispersion. Every molecule exhibits London dispersion. All right, what about dipole-dipole? HF, yeah, well, we look up here, right? We had HF as one of our examples. HF, remember, fluorine is much more electronegative. Just looking at the periodic table, right? Fluorine is going to have a much higher electronegativity. It's on the very top right of the periodic table than hydrogen. And so it's going to pull those electrons towards itself. So that's going to be a polar covalent bond or a permanent dipole, right? So yeah, HF, if it came in contact with another HF molecule, the partial positives on one of those hydrogens could be attracted to the partial negatives on one of the fluorines, and it could absolutely exhibit dipole-dipole. So dipole-dipole are also exhibited. All right, what about hydrogen bonding? Well, remember we said to know if a molecule can exhibit hydrogen bonding, we have to ask ourselves the question, is hydrogen on the phone? And so is hydrogen on the phone over here? Oh yeah, hydrogen's on the phone with fluorine. Okay, so it does exhibit hydrogen bonding. If another hydrogen or HF comes along, if another HF molecule comes along, it is also on the phone, right? So those two could exhibit hydrogen bonding. Absolutely. All right, let's try the next one. London dispersion, as always, every time. Dipole. What about dipole for H2S? So let's go ahead and draw the Lewis structure over here. So we've got sulfur bonded to hydrogen, and that sulfur still has those two extra pairs of electrons. Now we want to think about, all right, well, what is the shape of this molecule? So remember in our lab, we said that the shape of this molecule, we have 4 electron groups, 1, 2, 3, and 4. So the shape of this molecule, just like water, is going to be bent. Okay, so H, S, H, boom, 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 boom. And the reason for that is that these little lone pairs are going to kind of push those bonds away from them because they don't want the electrons near them. And we're going to get this kind of bent shape. Remember, this is just like water, right? You could draw water's Lewis structure the same way. And we know water has that kind of bent shape, right? So we've got this kind of bent shape for our H2S. So just we can look at a periodic table and we can say, well, it looks like sulfur is much further to the right than hydrogen. So I think sulfur is going to be more electronegative, and it turns out it is. And hydrogen is less electronegative. So when we draw our dipoles, we can draw a dipole arrow like this, where sulfur is kind of hogging those electrons on each of those bonds. And we can also draw a net dipole, where we kind of average, and actually I've drawn this kind of bad. Let me see if I can fix that. So we can draw a kind of net dipole, where we've got our kind of average of those two dipoles facing that way, right? If all of the electrons are kind of going over here on our sulfur, and they're kind of not hanging around our hydrogens, we're going to have a lot more electron density on this end of the molecule than on this end, right? And so overall, we have our partial negative on this top end of the molecule and our partial positive over by these hydrogens down here. And that's going to give us that difference in poles, or that dipole, that difference in charge at those poles. So yeah, I would say H2S is capable of dipole forces, or is going to exhibit dipole forces is a better way of saying that. All right, what about for hydrogen bonding? Is hydrogen on the phone? No, not on the phone here. It's on S. So even though sulfur is electronegative, it's not as electronegative as these ones. So it's not going to exhibit those really, really strong hydrogen bonds. It's not on the phone, so it's not capable of hydrogen bonding. So these are the two forces that H2S exhibits. And so I could also ask you the question, what is the strongest force, intermolecular force that O2 exhibits? And you would say London dispersion. That's as strong as it gets, right? It's the weakest, but that's as strong as it gets. For hydrogen, for HF, what's the strongest intermolecular force it exhibits? Yeah, hydrogen bonding, right? The strongest intermolecular force that HF exhibits is hydrogen bonding. And then for H2S, we could say the strongest is dipole. All right, now the strongest force out of all of these is, we said, ionic bonds. And this is when two ions of opposite charges are attracted to each other. This creates this really strong interaction. And these substances that are ionically bonded, they're very strongly held together. So they have these really high melting and high boiling points. And let's just think about what that means. If a substance has a high melting and high boiling point, that means that in order to get this thing to melt, you have to raise the temperature, right? High melting, high boiling. You have to raise the temperature really, really high to get it to melt. And even higher, right, to get it to boil. If a substance has weaker intermolecular forces, it's easier to get it to melt or boil. And so it's going to have lower melting and boiling points than something with maybe ionic bonding. And that's why when we look up here, all the way back up here, when we look up here at something like sodium chloride, right, notice how high those temperatures are, because sodium chloride is an ionic compound. So in order for a substance to enter something like the gas phase, for instance, particles need to be able to completely overcome the intermolecular forces that are holding them together. So if we look at our boiling points for these different substances, those that have these stronger intermolecular forces are going to have these higher boiling points. So looking here, we've got our substance, and then we've got the intermolecular force, the strongest intermolecular force that it displays, and then we've got our boiling point. Whoops. So for something like H2, the strongest intermolecular force, the strongest intermolecular force that H2 displays is London dispersion forces. So its boiling point is really low, negative 253 degrees Celsius. Really, really low to get it to go to the gaseous phase. And that's why when we find H2, right, what is H2? H2 is hydrogen gas. Hydrogen gas. When we find hydrogen gas, it's usually in the gaseous state because its boiling point is so low. Okay. Likewise, for something like neon. Neon is a gas. When you look on the periodic table, it's on the far right. It's in our noble gases category. It's a gas at room temperature. Well, why is that? Well, its boiling point is really, really low. In order to get it to go into the gaseous phase, we don't need to add any temperature, really, from our perspective, right? Here on Earth, when things are usually around room temp, right? So, and that's because its strongest intermolecular force is just dispersion forces. Okay, so really weak. And then you've got something, for instance, like water. Water's strongest intermolecular force, right? Hydrogen's on the phone, is hydrogen bonding. So in order to get it to boil, you do have to add quite a bit of heat. Have you ever tried to watch, your your water boil? Takes a while, right? You have to add heat. You have to add quite a bit of heat. And that's because those intermolecular forces that water exhibits are really, really strong. Not quite like an ionic compound, right? Not like NaCl where it's like 800 degrees Celsius, but still pretty high boiling point.